All right, let's take a look at this one. Here we have internal energy, heat, and work. So a balloon is being inflated to its full extent by heating the air inside it, so it's going to be expanding. So what do we know from that? We know that if it's expanding, that we're going to have minus W from the system's point of view. In the final stages of this process, the volume of the balloon changes from this smaller value to this larger value. So therefore, delta V is going to be a positive number of 0.50 times 10 to the 6th. I did that final minus initial subtraction in my head, and that was liters, by the addition of this much energy as heat. So what does that mean? That means that Q is equal to 1.3 times 10 to the 8th joules. Assuming that the balloon expands against a constant pressure, so you're even going to give me pressure of 1.0 atmospheres, which is going to simplify my math a little bit, I suspect. Assuming the balloon expands against, okay, got it. Calculate delta E for the process. So I feel two sig figs coming on too. So delta E is equal to Q plus W. And a more useful expansion of that, pun intended, is equal to Q plus negative P delta V, which is going to be equal to our Q value of 1.3 times 10 to the 8th joules, plus our negative P delta V term. 1 atmosphere times 0.5 times 10 to the 6 liters of my delta V. Again, I just did that subtraction from 4 to 4.5 in my head and got a half of times 10 to the 6th liters. Now, when I look at this, I can't add these terms together like they are right now because I got joules plus something called liter atmospheres. But that's why they gave me this conversion factor. So let's just toss it in there and say 101.3 joules per 1 liter atmosphere. Now I can perform a legal addition maneuver. Atmosphere, atmosphere, liter, liter. That quantity will come out in joules, and we're off to the races. So 1.3 second EE8 plus, open a paren, minus 1, why did I even do that? I don't even need that in there, times 0.5 second EE6 times 101.3. 7.94, if I wanted 3 sig figs, times 10 to the 1, 2, 3, 4, 5, 6, 7, which, if I want this in 2 sig figs, rounds to 8.0 times 10 to the 7, and all of that mess was in joules. So you could also write it in kilojoules if you prefer, 8.0 times 10 to the 4th kilojoules. Either one of those would be correct, a correct answer. Love it when I get the right answer. Doesn't always happen that way, as you've seen in the past. All right, so that's not that scary. It's really not. When you sit and look at, okay, can you do delta equals Q plus W? Of course you can. That's easy enough. You just got to pay attention to the signs. If you're going to mess something up, hopefully it's going to be the sign and not the concept. And then work equals negative P delta V. So they gave us a little bit of both of those. And then they gave us one where we had to use the whole shooting match all together with a conversion thrown in for good measure. So this would be very AP-esque. AP-esque, E-S-Q-U-E, AP-esque. So you should practice some of those. I believe the UT homework problems that we have will give you plenty of practice. So let's talk about enthalpy. We already talked about it a little bit, but it's really all you can do is to measure the change in enthalpy. Nobody has an enthalpyometer, so you have to perform a reaction, and you have to realize that delta H deals with this part of this graph. It has nothing to do with the activation energy part of the graph. That's what kinetics is all about, and we'll get to that soon, very, very soon. But delta H is what we call that state function, where it doesn't matter what path you took to get to school, it matters that you started at your house and you ended up at school. So it doesn't matter if you did it quickly and efficiently or if you took the long way by the donut shop and the 7-Eleven and Starbucks and everywhere else. Delta H equals Q at constant pressure, in other words, an open container. Because you're going to run into this in some lab questions, I want you to be ready for it. You ask yourself, container open? Yes. If the container's open, then delta H equals Q. And I can use Q equals MC delta T. It's true most of the time for us that we have an open container, and it's a very handy little fact to know. And the enthalpy can be calculated from several sources, including your good buddy stoichiometry, calorimetry, which I remind you is Q equals MC delta T, from tables of standard values that are usually given to you in heats of formation, from Hess's law, which we will do soon, and from bond energies, which we will also do soon. Here's the typo I was talking about. This question would be a better question if it asked what is the molar enthalpy change for the dissolution of 14 grams of KOH. So we're going to do a stoichiometry one. I know you're excited about it. Try to contain your enthusiasm. So here we go. Upon adding solid potassium hydroxide pellets to water, the following reaction takes place. So you put this in water, and we make KOH aqueous. So this is a delta H of solution, to tell you the truth. And it is positive coming off as a product, so you have to be careful with this. They wrote this as one big happy equation. So that heat is exiting as opposed to entering as a reactant. It's exiting the system. Therefore, it is a negative delta H solution. So answer the following questions regarding this. Does the beaker get warmer or colder? Well, if heat comes off as a product, warmer. You could feel that with your little bare hands. On the outside of the beaker, not the inside of the beaker, for heaven's sakes. Is the reaction endo or exo? Well, heat is exiting the system, so it is exothermic, which I remind you would have a negative delta H. What is then the molar enthalpy change for the dissolution of 14 grams of KOH? The first thing you got to do is get that into grams, get it into moles. So you need a handy-dandy periodic table. Surely you have one close by. If not, then I'll show you mine, and then you can pause it and you can calculate that molar mass. I have to make it a little smaller for you. There you go. Calculate your molar mass. Go ahead, pause me. KOH. Okay, so you should have come back from being paused and calculating your little molar mass there. And you should have come out with the fact, I'll put this back on 125. Oops, what happened? You've got how much moles, how many moles do you have? You've got 14 grams of KOH divided by that molar mass that you calculated of 56.11. So that's going to get me moles. And the fact that 14 grams was added to water. That's where I came up with that. And the heat that exited was 43 kilojoules. We should come out with 14 divided by 56.11 times 43. 10.7298. How many sig figs do we want? I see 3. I see 3. I'm going with 3. So I'm looking at my calculator, and I see 10.7. So 10.7 is the absolute value in kilojoules per mole. But what should we put on it as a sign? Well, it got warmer because it let heat out of the system, as it shows us right here yet again. So you've got to supply the negative on that number, and that's what's going to get you. I'm telling you now, you're going to make a mistake, but it's okay, because everything I know, I learned because I did something wrong. So I don't think making mistakes is a bad thing. You just don't want to do it on quiz and test. You want to practice enough to get all that out of your system before you take a quiz or a test. All right, so you've heard me talk about calorimetry. Let's get down and dirty with the details. I'm going to minimize this for a few minutes, maximize that. Calorimetry is defined as the process of measuring heat based on observing the temperature change when a body absorbs or discharges heat, or energy rather, as heat. So there are two kinds. The kind that you're probably going to do in class, because very few chemistry labs at the high school level have bomb calorimeters. You're going to probably do a couple of coffee cup, like little polystyrene, brand name styrofoam coffee cup nested in with one another so you get super duper insulation. And that's how we usually do it. So we're going to find the energy of a particular system. We use that styrofoam cup and the reactants that begin at the same temperature. So you want, hopefully your teacher would have made or you would have made the chemicals early enough that they got to sit for a few hours, or ideally overnight, so they're at the same temperature and have reached what we call thermal equilibrium with the room, so that you can assume they are room temperature. But you should still use a thermometer and measure to make sure. After all the data is collected, whether you did mass or volume, initial, final temperatures, all that stuff, we can use this specific formula to find the energy released or absorbed. So if you used mass, if any of your reactants in your coffee cup were solids, then you're going to need to know grams divided by molar mass to get to moles. But if they were solutions and they were aqueous, then what are you going to need? Well, you're going to need the density. So you're going to need the fact that density is equal to mass per unit volume, right? Isn't that right? Yep. So I want to solve for volume. So volume is equal to mass divided by the density. So you just want to make sure that if you get the density, that you use that calculation correctly so that you end up getting the volume. I'm sorry, you end up getting the mass from this. I'm so sorry, I did that wrong. The mass would be equal to for the density times the volume. That's much better because you want the mass. Because, why do you want the mass? Because Q equals M for mass, C delta T. All right, let's talk for just a minute about the units on C, because if you were introduced to this in first year chemistry, and I certainly hope you were, this was probably your very first introduction to a constant with ridiculous units. If we rearrange and solve Q equals MC delta T for C, what do we get? We get Q divided by M times delta T. So the units on C are going to have to carry the energy unit for heat, which is a joule. Could be a calorie, but joule is what we normally use on the AP exam. And a mass, which is most likely a gram, and a unit of temperature, whether it's degrees C or whether it's Kelvin or whatever. But all of those units have to be in here to make this a true statement when we start multiplying things together. Because Q is measured in joules, mass is measured in grams, T is measured in, I'll stick with degrees C for now, because it's lab. You've got a centigrade Celsius thermometer. So, does a gram times a delta C equal a joule? Oh no, in the mathematical world as we know it would come to an end. So we have to throw in a number, which is, C has a numerical value, a magnitude so to speak, but we have to put in these goofy units so that that cancels that, and that cancels that, and now joules equals joules, and all is right with the mathematical universe. So I just wanted to have that little side talk for a minute. So coffee cup calorimetry, by far the one you're going to do in lab. You should do a calorimetry lab. Probably have already done them in first year. If so, you probably should go back and review it, certainly before the AP exam. Then bomb calorimetry is where we place the reactants inside a steel container and ignite it. This is done a lot with food sources in the food industry, so that, you know, all those calories that you see on the package, they're not real calories in the chemical sense. They're actually kilocalories. But they make sure and capitalize the word calorie, which is sneaky, I have to say. But yet, it is sort of depressing to consider that my Snickers bar that I like so much has 325, not just calories, but kilocalories of chemical energy in it. So it would probably deter me from eating as many. Or so you would think, anyway. So, often we refer to this as constant volume calorimetry. So when we're doing the coffee cup, it's Q equals MC at constant pressure, delta T. And when we do the bomb, it's Q equals MC constant volume, delta T, but because we know the mass of the container and it's never going to change, we combine these two terms and often simplify this into a capital C, delta T. Almost looks like the word cat, doesn't it? All right, so we do that a lot. So, recap, for those of you that are verbal. Heat capacity, energy required to raise the temperature by 1 degree. So it's usually measured in joules per degree Celsius. So heat capacity is the energy required to raise 1 gram of a sample by 1 degree. Actually, I'm sorry, that's specific heat capacity, which we're going to get to down here. I got ahead of myself. Heat capacity, we don't specify an amount. It's coming. Specific heat capacity is the same as above, but like I said, specific to 1 gram of a substance. So specific heat is the quantity of heat transferred divided by grams of the material times the degrees of temperature change. And that's where we come up with these ridiculous units. So we can do this in moles, we can do this in mass, we can do this in joules, we can do this in calories, we can do this in Kelvin, we can do it in degrees Celsius. Technically it's not degrees Kelvin, you know, it's kelvins. Energy, that's my Q value, is released or gained at constant pressure, and like I said, Q equals mc delta T, and if you're in an open container, it's constant pressure. That's what the little P's in there for, not big P for like the pressure of the room or anything. So the specific heat of water, which if you're in physics is also called the mechanical equivalent of heat, is 4.184 joules per gram degree C, or 1 calorie per gram degree C if you need to convert back and forth between these two. Water has one of the highest specific heats known, which is fabulous, fabulous. Fabulous news if you're a fish. Because if you're a fish and it's the fall and the weather's getting colder and colder and colder outside, the water temperature is getting cooler and cooler and cooler, and if it gets cool enough, wouldn't your water freeze? Eventually, yes it would. Except that the density of water is also a weird thing because it's not most dense at its coldest. Ice actually is less dense than water. Come on, don't pretend that's a newsflash. You have seen ice cubes floating before. So we make an insulative layer of ice on the top of a pond without the pond freezing all the way solid, so the fish can survive. They may be cold and a little bit grumpy, but they can survive. And then when spring comes, the ice cap begins to melt, and then the water will begin to warm, and the fish are happy again. So water's high specific heat really helps give us a thermal equilibrium in a lot of different ways in our atmosphere. One of the overlying principles of what you're going to deal with in solving problems is heat lost equals heat gained. That's obeying that law of conservation of energy. If somebody lost heat energy, somebody else had to pick it up, or else we're going to mess up the universe. And if this doesn't happen, then you can usually calculate the heat capacity of the substance. All right, so units of energy. The calorie, again, is the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius, which is the same as raising it 1 Kelvin of change Celsius, I must say. The kilocalorie is that, again, that food calorie with a capital C. And kinetic energy, which you may encounter as well, is 1/2 mv squared, and it's kilogram times meters per second squared as its units. And then the joule is the SI unit of energy, and 1 calorie is equal to 4.184 joules. So joules are a smaller quantity than calories. And it's cool if you ever get a chance to go over to Europe and you get to look at the soda pop can for, say, a diet drink, like a Diet Coke. Instead of it saying 0 calories, it's going to say like 2-point-something kilojoules. Or 2-point-something, no wait, 4-something joules? Anyway, it's going to give you a value in joules that ain't 0. Because when we round this up to kilocalories, and you round, it's essentially 0 in kilocalorie units. But when joules are a smaller unit, you can't round it to 0. So there really is some heat energy in there. It's kind of a sham what we do here in the U.S. All right, in a coffee cup calorimeter, 100 milliliters of 1 molar sodium hydroxide. I've been begging you and begging you, if you've listened to any previous recordings, to embrace the fact that molarity times volume is moles. So if I have 100 milliliters of 1 molar, that's 0.1 liters of 1 molar. That's 0.1 times 1, which is going to be 0.1 mole of NaOH. And, same song, second verse, 100 mils of 1 molar HCl, which is also 0.1 liters times 1 molar, which is 0.1 moles of HCl, are mixed. Both solutions were originally at this temperature. So T initial, 24.6 degrees Celsius. After the reaction, the final temperature is 31.3 degrees Celsius. Delta T is in my future. Assuming that all solutions have a density of 1, well, that made it easy, gram per centimeter cubed, and a specific heat capacity of this, so C equals 4.184 joules per gram degree C for these solutions. Calculate the enthalpy change for the neutralization of HCl by NaOH. Assume that no heat is lost to the surroundings or the calorimeter, which is pure fantasy, but we'll humor them and assume that anyway. Alright, so what you got? What you gonna do here? Let's get that delta T first, maybe? Well, I can throw it all into one big hairy calculation. Q equals 200 grams. There's my mass. So I should do it that way, shouldn't I? Don't get ahead of myself. 200 grams. How do I know that? They told me the density was 1 gram per centimeter cubed, and I didn't fall for the fact that a centimeter cubed is not the same thing as a milliliter, because you know good and well it is. So this could have very easily said milliliters right there. So 100 milliliters is going to have a mass of 100 grams. And if I had 100 grams and 100 grams, then I have 200 grams. C was 4.184 joules per gram degree C. And delta T is final minus initial. And because this is at constant pressure, this is also equal to delta H. I had to reread the problem real quick. All right, so what do we got? $200 times 4.184 times, you can either figure it out ahead of time or you can just do it right here, 31.3 minus 24.6, your call, equals a lot. 5606. How many sig figs do I need? I see 3, 3, 3, 4, 3, 3, 3, 3. I'm going with 3. Oh, no, they gave me a density in 2. That was tacky. Give me a density in 2, so that's 2 sig figs. Making sure I typed it right when I typed it down here, which I did. All right, so what do we have? We have 5606. Let's clean up units. Gram. This entire parentheses came out in degree C, right? So I'm not cheating by doing that. So I come out with joules. I need 2 sig figs. 5600 joules. And so you may rather report it as 5.6 kilojoules per mole. Where did I get the mole? Actually, I don't have the mole. I'm just going to have to do it that way. So that's really wrong. It really should be kilojoules, because they didn't give us a full mole to work with. I could figure it out, but that's not what they asked me. They asked me what was the change, calculate the enthalpy change, which I did. Okay, I don't like the fact it's not in a quantity, but that's the way they wrote the problem. All right, so exercise 4, more enthalpy. When 1 mole of methane is burned at a constant pressure, 890 kilojoules per mole of energy is released as heat. So that's either Q or that's delta H, because it says at constant pressure. Calculate delta H for the process in which a 5.8 gram sample is burned at constant pressure. Okay, so this is just dimensional analysis. Can you go from the fact that there's 890 kilojoules released for 1 mole versus how many moles you have, which is 5.8 grams divided by a gram per mole, which is going to give me a 1 over 1 over mole, which makes it mole, and then moles cancel, and I get kilojoules? Just dimensional analysis. So what is the molar mass of CH4? 12.01 plus 4 times 1.01 is 4.04, 16.05. So that times 5.8. Oh, where'd I get, wait. Oops. Should have done that the other way around. 5.8 divided by, go up and get it. I love the new operating system. There we go. There's my moles. So it's a fraction of a mole, as expected, times 890. A little bit of common number sense goes a long way with these two. So I come out with 321.6. How many sig figs do I need? I see 2. I see 2, so I'm going with 2. So, first of all, it's burned. That's hot. Right? So this is XO. So I'm going to put a negative sign on it because they want delta H. Right? That means I need to worry about the sign. They didn't want Q. They want delta H. And so that's going to be negative. I'm going to report what's in my calculator is 320. And its units are kilojoules per mole. I know what you're thinking. You're thinking this mole cancels out that mole. But you know what? It's really per mole of reaction. You need to get in the habit of reporting it as kilojoules per mole. So negative 320. Now I'm going to get a little more sophisticated here. I'm going to throw some stoichiometry in here too. When 1 liter of 1 molar, okay, molarity is moles per liter times 1 liter, that's 1 mole, of barium nitrate solution at 25 degrees Celsius is mixed with 1 liter of 1 molar, that's 1 mole, of Na2SO4 solution at 25 degrees Celsius in a calorimeter, the white solid barium sulfate forms and the temperature of the mixture increases to 28.1. Delta T, I could do in my head, right? What's the difference there? 3.1 degrees Celsius. It also increases, so I know I'm going to have a negative delta H, so I need that negative sign. Assuming that the calorimeter absorbs only a negligible quantity of heat, that the specific heat capacity of the solution is this, there's my C, and the density of the final solution is 1 gram per mil. Calculate the enthalpy change per mole. Calculate the enthalpy change per mole of barium sulfate formed. Okay, I need an equation. Ba 2 plus SO4 2 minus. I'm going to do it net ionically. BaSO4. So 1 mole bounds. So what am I going to make? 1 mole. But you need to do the stoichiometry to be sure. So Q is equal to delta H in this case because it says constant pressure somewhere. And that is going to be equal to MC delta T. So what am I going to make? Well, what's the mass of this whole mess? The mass of this mess is the fact that 1 liter is 1,000 grams and 1 liter is 1,000 grams. I have 2,000 grams taking place here. And that times 4.184 joules per gram degrees C times my temperature change of 3.1 degrees C. See, I had to come back to grams of solution because of this gram right here. If they had given it to me in moles, I would have been happy using the moles, but it didn't work out that way. So, good Lord, how many sig figs do I need on this? 2 because of this density. Again. So, I'm going to clear off that last mess. 2,000 times 4.184 times 3.1. What do you get? A big old number. How much of it do I need? I need 2. So that is equal to negative 26,000 joules, which is negative 26 kilojoules per mole. Oops. There we are. Okay. This works out way better when you try the problem yourself first. So let's see what we have facing us next. Constant volume calorimetry. It has been suggested that hydrogen gas obtained by the decomposition of water might be a substitute for natural gas, which is principally methane. To compare the energies of combustion of these fuels. That's my goal. Compare the energies of combustion of these fuels. The following experiment was carried out using a bomb calorimeter with a heat capacity of, so that is my big C. Notice it's got kilojoules per degree C. When a 1.5 gram sample of methane was burned, the temperature increased by 7.3. There's my delta T for methane. When a 1.15 gram sample of hydrogen gas was burned with excess oxygen, the temperature was increased. There's my delta T for hydrogen. So they gave you everything here. So the best thing to do is calculate for methane, calculate the energy of combustion per gram for both and methane. Okay, so let's do methane, CH4. What'd they give me? 1.50 grams gives Q equal to C, that's the big mass of the calorimeter times the specific heat of the metal it's made from, delta T. So Q equals 11.3 kilojoules per degree C times the number of degrees C it increased, which they told me was 7.3. So Q of methane. (11.3) times 7.3. And I get 82.49. Now here's the rub. So 82.49 kilojoules, because my degree C is canceled. But you got to realize that that isn't a fair fight, right? Because calculate the energy of combustion per gram. So this was really done per, how much was this sample? Methane was 1.50 gram. So I need to really come back and make it per gram by dividing by the fact I had a 1.5 gram sample. And I get 54.99. Let's call that 55. 55 kilojoules per gram for methane. Let's see what I get for hydrogen. How much did I burn? 1.15. And Q is equal to that big C, delta T, looks like cat. Alright, and it's still the same bomb, so 11.3 kilojoules per degree C times how much temperature here? 14.3. So that Q comes out to be 1.3 times 14.3, 161.59. Those cancel, so that's kilojoules. And how big was this sample? 1.15. So divided by 1.15, 140.5. Let's call that 141 kilojoules per gram. Now that's what they asked me to do, which is kind of silly because what they really should have done is said which is better. So what do you think? Huh? What do you think's better? You think methane's a better fuel than hydrogen? I don't think so. Right? Because you're going to get 141 kilojoules per gram for every gram of hydrogen versus 55 kilojoules per gram for every gram of methane. All right. Here comes the big mama equation. There are these tables in the back of your book, and the thing called the appendix in the back of your book. There's some good information in the appendix in the back of your book. And these tables are about the enthalpy of formation. So we take compounds and form them, the elements, in standard state. In other words, if it's a halogen or any gen at all, hydrogen, oxygen, nitrogen, or any of the halogens, they're going to be diatomic. You're also going to respect whether they're solid, liquid, or gas. So we're talking room temperature, 1 atmosphere pressure conditions here. So all of those numbers in the tables, this is an abbreviated table sitting right here, but all of those numbers are done in kilojoules per 1 mole. How much? 1 mole of the compound. So It is defined as being 0 for elements in their standard state. So you do a happy dance every time there's an element in any chemical equation you see, because you know it's delta H sub F, its heat of formation, is a big, fat, beautiful, round, symmetrical 0. So we have Hess's law. I lovingly refer to it as the Big Mama equation. You don't have to do that, and for the love of God, never write that on the AP exam in your free response. You can think it, but please don't write it. It's really called Hess's law. But Big Mama equation is way more fun. All right, and it's simply the delta H of the reaction is equal to the delta H of the products minus the delta H of the reactants. So this problem is asking us to calculate using these tables, and this happens on the AP exam a lot, even in multiple choice. In multiple choice, you would round these numbers. That would be minus 300, that would be minus 1700, that would be minus 700, that would probably be 100. You can work with 90, but 100 might be easier, and that would be about negative 250. Those numbers would be much more math friendly without a calculator. And then if you round it up when you did your estimations, know that pick an answer a little bit less than what you calculated out with your estimations, and vice versa. So here's a big hairy equation, and they want us to calculate the delta H naught for this reaction. All right. What are we going to do? Well, first thing I'm going to do is I'm going to look for elements because they simplify my life. There's one. Dang it, that's the only one I got. Okay, so at least I don't have to deal with aluminum. Aluminum's delta H value is 0. So I write the Big Mama equation in its most elegant form. Delta H, try that again. Delta H of the reaction is equal to the sum of the delta H of the products minus the sum of the delta H of the reactants. That's the Greek capital letter sigma, if you're not familiar with it, and in mathematics and science it stands for the sum of. It means add them up. All right, then my next step is to actually identify who the heck I'm talking about here. So who are the products? There's one. I don't like to put the parentheses at this stage. Some books do. AlCl3 is another. 3 times NO, and 6 times H2O. Those are all the sum of the products minus the 3 times the NH4ClO4, ammonium perchlorate. And I don't have to do the aluminum because its value is a 0. It simplifies my life a little bit. I like to write it that way, especially when I'm first teaching it and you're first learning it, because it's visually easier for you to match up the numbers and not make a goof at this point. So I come to the table. I find Al2O3. I write down its value. And I add it to AlCl3's value. I'm going to worry about units later. They're all in kilojoules per mole. I know that makes you happy if I'm going to be lazy. And then, 3 times the next set of parentheses. NO, 90. Notice it's a positive value where the rest have been negative. And then 6 times water, which is a negative 242. That's a big old giant chunk of numbers. Minus 3 times the ammonium perchlorate, negative 295. Okay, let the calculator extravaganza begin. Open a paren, use your negation sign, and just get at it. Plus a negative 704 plus 3 times a positive 90 plus 6 times a negative. My 6 didn't register, did it? I didn't hit the key hard enough. Dadgummit. Sorry about that. Technical difficulties. I got a plus times there. 90. Where was I? I left off at 90. 3 times 90 plus 6 times negative 242. Okay, hopefully I got it in there right that time. I'm going to close that paren. So I just entered all of this gobbledygook minus, I like to open a paren. You don't have to. I'm I just make fewer mistakes when I do it this way. 3 times a negative 295. In other words, visually, I make it look I put it in the calculator exact same way it's visually written on my paper. But some of you are smarter at math than me. So I get negative 2,677, and I look back up here at the table to see that that is all kilojoules per mole. And there we have it. So that's one way to do Hess's law. There's another way to do Hess's law where we're going to add a bunch of series of chemical equations together, and we'll know values for the entire equation. So we basically have two different varieties for this. So Hess's law, Big Mama equation, is simply take all of the product heats of formation, add them up, remembering to multiply by their coefficients, subtract from that big giant sum all of the heats of formations added together in a big giant sum, and the difference between them, respecting the sign, is going to show you what's going on in that whole entire chemical reaction. So that negative sign means this is exothermic. Alright, so let's look at this one. Sometimes all values are not found in the table of thermodynamic data. Believe me, this is a favorite tact in the free response on the AP exam. So get good at this technique because you're going to have to do it over and over again when we start working AP problems. For most substances, it's impossible to go into a lab and directly synthesize a compound from its free elements. The heat of formation for the substance can be found by working backwards from its heat of combustion. So we want to find the delta HF of C6H12O6. That sounds somewhat familiar. I think I know that compound. Glucose. From the following information, glucose plus 6O2 yields 6CO2 plus 6H2O. For the love of God, you should recognize that as well. What is that? That is the equation for, drum roll, cell respiration. Alright, so what are they telling me? You've got to learn to decipher this code. We've run into it now for the second time. If they toss onto the end of all the chemical gobbledygook a value in energy units such as joules or kilojoules, they just told you the energy for the reaction. What you have to lock onto like a heat-seeking missile is, did the heat come out as a product, in which case it is XO, negative sign on that delta H, so it's negative 2,800 kilojoules. So it has, let me try that again. Delta H is equal to negative 2,800 kilojoules. It has a negative delta H, was my point. Now, if you see it on the other side coming in as a reactant, that heat quantity, then you know it's endo. It's going to have a positive sign. So they told me the delta H of the reaction in a roundabout way. So I can use the Big Mama equation, Hess's law, and I'm again praying for some elements here. There's one. That means that value is 0, and the rest are all compounds. So the delta H of the reaction is equal to the sum of the delta H of the products minus the sum of the delta H of the reactants. You are wise, very, very, very wise to write that on your paper before you ever start the problem, because it's sometimes worth, more often than sometimes, it's often worth a point on the AP exams. Don't be too lazy. Plus it helps guide your thought process. Alright, now I can plug and chug some things in. I know that this is negative 2,800 kilojoules. It's going to end up being per mole, as all delta H's are. Equals, now I'm going to do the chemicals. 6 CO2s, 6 H2Os. All of that's bracketed as my products. So now I subtract the reactants. There's only one to worry about, and that's my good buddy glucose. And now I'm going to actually come in and plug in the numbers. But I really want to solve for this quantity, right? Isn't that what I'm looking for? Let me reread the problem. Sometimes you have to reread the problem. Yeah, because all I've got is this value and this value. So I'm looking for glucose. So if I move glucose to this side of the equation, it becomes a positive entity of C6H12O6 delta H thereof. Let me try to write that a little neater. Delta H of C6, fat pen, C6H12O6 is equal to. So I just got rid of that minus sign right there by moving over to the left side of the equation, the entity I'm looking for. I'm going to do the same thing. I'm going to stick with this, but I'm going to go ahead and say 6 times the CO2 value, 6 times the H2O value, and wouldn't I add 2,800 at this point? Everything's in kilojoules per mole here. So I go up the table, I find CO2, it's a negative 393.5. I go up the table, I find the H2O, it's a negative 285.8. And that means that the delta H formation of C6H12O6 is equal to, clear screen, 6 times minus 393.5 plus 6 times negative 285.8, hopefully I punched all the buttons right, equals the bracket amount, negative 4075.8, and I add to that a lovely 2,800. And I come out with negative 1276. I'm going to keep in line with 4 digits, yes. Kilojoules per mole for glucose. So, can you do add, addition, subtraction, distributive property, etc., and solve for one of the critters in the Big Mama equation? Alright, so exercise 10, using enthalpies of formation, calculate the standard change in enthalpy for the thermite reaction. But you weren't given any data, so you're going to have to use your book. So put me on pause, go look up what you need. Always being on the lookout for your good buddy's elements. Ah, found one. Found another one. So all you really have to look up is Al2O3's value. That's the product minus the reactant, Fe2O3. Go find them. Put me on pause. All right. The values I'm about to write down may be a tad different from the values in your book or what you might have gotten off the internet. I do not want you fretting over the fact that I'm about to write negative 1676 in kilojoules per mole, and your book had 75 or 80 or whatever. If it's in this neighborhood, they're in good enough agreement for what we're doing here. We're not doing rocket science just yet. And then I have a negative 826 for the iron 3 hydroxide. So now, can you just use your calculator properly? Negative 1676 minus negative 826 equals negative 850. And all the values were in kilojoules per mole. And you probably need 3 sig figs, so throwing that decimal point on the end of that makes it 3 instead of 2. And there you have it. Alright, so that's Hess's law. You getting it? Hess's law is simply the delta H is equal to the sum of all the products, heats of formation, minus the sum of all the reactants, heats of formation. And you go look them up in a table. Paying attention to signs ever so terrifically. Now, this one is the other value of Hess, the other way to do Hess's law. Hess's law works also with systems of equations. So enthalpy is not dependent on the reaction pathway. If you can find any combination of chemical equations that are going to add up to give you your desired overall equation, then you can also sum up the delta H's for the individual reactions. So I want you to go in your brain right now to that part of algebra, especially algebra 2, where you learn to solve systems of equations. If you've had physics or are currently in physics, it's the same part of your brain that you deal with when you're doing projectile motion and you have 2 unknowns. If you have 2 unknowns, then you need 2 equations and you solve as a system of equations. In other words, we're going to have like equal sign things, and if something's on both sides of the equal sign, it's going to cancel off. Even if it's this way, it's going to cancel off. If it's this way, you can even do this. You follow? Systems of equations. But we're not going to have equal signs. We're going to have arrows in chemical reactions. Same part of your brain, though. You know how to do this. This is not a new skill. It's an old skill applied to a new situation. I know you love that. All right. So remember this. First, you're going to have to decide how you're going to rearrange the equations so that your reactants and products are on the appropriate sides of the arrows. In other words, if I am given an equation with water on the left and I need water on the right, I've got to flip the equation. When I flip the equation, I will change the sign of the reaction. So if it was a negative value at first, it's going to become a positive if I flip it, and vice versa. If the equation had to be reversed, like I just said, reverse the sign of delta H. If the equations have to be multiplied to get a correct coefficient, then we're going to multiply the delta H because, remember, delta H's are in kilojoules per mole. Remember, stoichiometry implies moles as well. That's 3 moles of water, not 1. So since this is a 3 and this is per mole, I would have to triple this if I need to. Check to ensure that everything cancels out to give you the exact equation that you want. I call that my goal equation. And it's often helpful to begin your work backwards from the answer that you want, which is why I call it my goal equation, because the answer that I want is my goal. So let's see if we can tackle this big, bad, ugly situation right here. All right, what do we want? We want to have water on the right, B2O3 on the right, and H3BO3 on the left. Okay, the first equation has water on the right. That's a good start. It has HBO3 on the left. That's a good start. The next equation has something in it that doesn't even belong at all in my goal. So I look at the third one and see the same blasted thing. So one of those is going to be switched because somewhere I've got to cancel out that H2B4O7 because it's not my goal equation at all. And this is what I call my goal for this overall reaction. I call it my goal equation. All right, so which one am I going to flip? Tricky. At first glance, it's got to be the second one. Why does it have to be the second one? Because I need B2O3 on the product side, and in the third equation it is, and it's not anywhere else in any of the other equations to be canceled out by that. So my thought process is going, I need water on that side, good. I need that on that side, good. But this is bad. One of those has to be switched. So my first attempt at this is going to be to flip this one, so that I'll get H2B4O7 on the left and H2B4O7 on the right, so it can be canceled out. That's also going to put more water on the right, and I need 3 of them, so this could be a good thing. So that's my first inclination. So I just have to do some rewriting here. I'm going to leave this first one as is. I also like to line up the arrows. Give yourself plenty of room on this. All right, then I'm going to flip the next one. So I'm looking at the arrow, which means I'm going to put 4 HBO2s over here. And that's a good thing, because that's going to cancel out that HBO2 right here, which also does not appear in my goal. I just got some math to do when I'm done. And I'm going to make H2B4O7 and some more water, which is a good thing, because I need 3 of them. And then I'm going to leave the bottom one for now. I'm just rewriting it so I can scribble all over it and line up my arrows. Okay, so if we attack this, what are we going to do? Well, the whole reason of doing this was I really needed to get rid of this guy because it's not in my final equation. And then I really need to get rid of HBO2 because it's not in my final equation either, but isn't that going to require me doing this? Yes, it is. So now I can do that. And now do I have at least the players where they belong? H3BO3, yes, and that's all that's on the left. B2O3 and H2O is all that's on the right. I realize my quantities aren't good, but let me clean this up and then I can deal with my quantities, because I think you can already see what's going on here. Our mess is doubled. Okay, so there's my overall equation from adding these three puppies together. But it's twice my goal, right? Because 4 is twice 2, and 2 is twice the 1 that's understood there, and 6 is twice 3. So I'm going to do the math side, and then I'm just going to cut my answer in half. So to do the math side, that one that I flipped, the one I flipped, I changed the sign. The rest, I just add up. Because I did not, I did multiply the first one through by 4 as well. So this quantity is going to be multiplied through by 4. See my 4s? I had to go through and quadruple everything on the top reaction. I didn't flip it, so I'm not going to change its sign. So this becomes a delta H reaction of 4 times negative 0.02. It's all in kilojoules per mole. I'm not going to sweat the units at this moment. This one stayed the same in terms of quantity, but it was flipped, so it becomes a positive 11.3. And then what's this one? Did I do anything to it? Nope, left it just like it was, so it's still a positive 17.5. So you add that up, and that's the delta H so far. So isn't 4 times 0.02 0.08? So add all of that up. For safety's sake, I'm going to go ahead and use my calculator. I realize I could do it in my head, but 28.88 kilojoules for this mess, but cut it in half. How come? Because my goal equation is half as much. So therefore, delta H for this reaction is equal to 1/2 times what I got for twice that much quantity of matter, which is going to be 14.44. 14.4 for 3 sig figs. Kilojoules per mole. And it's got a positive sign. It's endothermic. So once again, what do? If you flip a reaction, you change the sign. If you multiply a reaction, you multiply the delta H. If you divide a reaction, you're going to divide the delta H. So whatever thou does to the reaction, thou must do to the delta H. If you flip it, you flip the sign on the delta H. If you multiply the delta H. If you divide the delta H. Don't try to make that hard. All right, final topic coming at you, bond energies. So we got to clear up some misconceptions. Amazingly, across this country, science books plant these misconceptions. It takes energy to break bonds. Energy is released when bonds are formed. A lot of early science books talk about energy stored in bonds, which leads to this fuzziness. So it's very, very simple. You're going to break it apart, you're going to have to exert some effort in the terms of energy. When something new is formed, energy will be released as a new combination is made. The thing is, you got to account for was more energy expended or was more energy released. That's the delta H. So this delta H is the sum, again with that big sigma, the sum of the energies required to break old bonds, which are all going to bear positive signs because you're adding energy into the system to break those bonds, plus the sum of the energies released being a negative sign, in the formation of new bonds. So I think of this as cost, and I think of this as payoff. What did it cost me, and what's the payoff, and do I have a net gain in energy? So it's very helpful to draw these out. You don't have to. You can do this simply algebraically, but I think for this example, I'm going to draw it out so that you can visualize what's going on. H2 looks like this. F2 looks like this. And HF looks like this. Oh, but we have 2 of them. So, what did it cost you to break that HH? 432. What did it cost you to break that FF? 154. What were you paid in terms of making those HFs? Twice 565. So what was your cost? 432 plus 154. What was your payoff? You were paid more energy. I can eyeball it and tell, right? So that value was 2 times 565. So that's my payoff, which is greater. So what's the difference between these? $544. That's the difference in absolute value anyway, is 544. Your brain may have to put the negative sign on it. I structured it algebraically, luckily for that, but not necessarily always going to happen that way. But you just have to think, what did it cost me to break the bonds? What did I get as a payoff when new bonds were formed? If this number, 586, is less than this number, which was 2 times 565, and you can eyeball that and tell it was, then exothermic. In other words, you got more energy out of the system than you put in, so energy left the system, and that's going to be my delta H. So my delta H is negative 544 kilojoules per mole. Again, I'll slap you with my units because everything's in kilojoules per mole. All right, so let's do a quick little summary. Sorry, I went too far. Quick little summary for enthalpy. What does it really tell you about an equation? If the delta H is positive, the reaction is endothermic. Energy is added into the system. If the delta H is negative, the reaction is exothermic and heat energy is lost from the system. This is what is favored in nature because nature tends toward a lower energy state. And I leave you with these classic graphs you will see over and over again in this course. You have already seen them over and over again in other courses. And I want a quick interpretation of this. Energy is on this side. Time, reaction progress, reaction coordinate, lots of different labels for that x-axis. I kind of am a fan of time, but here's the difference. This is your reactants. This is your products. Isn't it a visual thing for you to see that we started off at a high number and we ended at a low number? Therefore, energy exited the system. Whether I call it delta H or whether I call it delta G, anything that's measured in joules is coming out of there. So I can use all different symbols. I can use E, H, G. Grown-ups can't get along. In the context of the problem, it works a lot of different ways. You've seen this in biology class where we come along and do this, and we put in a catalyst, and it lowers this thing right here, which is called the activation energy. Notice the activation energy doesn't have a dang thing to do with that delta H value, and that's important for you to realize. I still have an activation energy on this side. If I add the catalyst, it makes it a lower value. But these are my reactants. These are my products. Started off low, ended high. That means they had to have absorbed energy from low to high, from here to here. So that added energy into the system. So there are not a tremendous number of AP problems that deal with just calorimetry. It's an excellent topic for multiple choice questions, though, and you want them because they're easy. So what's going to happen next is I'll do another recording, but it'll be on the second half of thermodynamics, which will deal a lot with delta H's and delta G's and the other laws of thermodynamics. This chapter was all about the first law. And when I do that, then I will create some files about how to answer the essays of AP problems, and that's where you should start, because all of the basic concepts are buried in the essay questions. The problems are actually fairly straightforward and easy. It's the essays that's going to kill you, because if you get an essay, you're not going to know how to write about this energy stuff. Trust me, I've graded thousands of these papers and they all suck. So I want to get you sorted out on your responses so that you don't suck. And then I also want to make sure you understand that the math side of this is a lot of plug and chug, and so that's easy. So there are several more recordings in your future should you be so inclined as to spend more time with me. Thank you very much for your kind attention, and I wish you a very good day.